All right. So today's class is going to be kind of an introduction to astrodynamics using FreeFlyer. So we're going to learn a little bit about astrodynamics and a little bit about FreeFlyer. So first, we're going to start out by taking a look at FreeFlyer, which again, if you haven't downloaded yet, please go ahead and register on our website. All the instructions are both in the chat that Michael posted and also in Matt's original emails. If you don't want to follow along on the hands-on examples today, that's totally fine too. You can just watch the workshop for the content, but I would definitely recommend downloading FreeFlyer when you get a chance and then going back and working through the examples yourself. It's a great learning experience and it's free. After we see FreeFlyer for the first time, we're going to just go over some basic astrodynamics concepts. So to anybody who's already taken an orbital mechanics class, that might be a little bit of review for you. So feel free to tune in and out at your leisure. Then we'll walk through a couple of hands-on examples in our FreeFlyer University Guide. And then at the end, we'll just kind of round off with a summary of what FreeFlyer does, some of the more advanced capabilities, things like that. So first of all, you may or may not have heard of AI Solutions. So AI Solutions is a small business in the aerospace industry. For this group, we want to point out our Women in STEM initiative. So I would definitely recommend checking that out on our website. We have a lot of really awesome female employees doing really cool things. I'm not on there yet, but I'm sure I'll make it one day. We do a lot of different things within the company. FreeFlyer is a part of that. So we produce FreeFlyer, which is our product, but we're also contractors for companies like NASA, Lockheed Martin, Northrop Grumman, big Sierra Nevada corporations, lots of big companies across the industry. At all of our different offices, we do a lot of different things as well. So up here in Lanham, we do a lot of work over at Goddard and things in the area. Down in Florida, we do launch services. And we're just kind of spread out all over the country. You can see we've won a number of exciting awards as well. So I work on the FreeFlyer software team, and FreeFlyer is our biggest product for the company. So it's a software that is designed to provide support for the full mission lifecycle. So just from starting basic, defining your orbits, basic mission planning, all the way up to operations and supporting orbit determination and processing telemetry data and things like that. So you can start out building your mission up in FreeFlyer just with the absolute basic modeling, and then eventually turn it into a real life satellite flying in space. Again, a lot of people haven't heard of AI Solutions because we're a smaller company, but we're actually very well established. We've been around for a long time. FreeFlyer is at 23 years now. And as you can see, all of these missions on the right side of this window are currently being supported by FreeFlyer. So some highlights that you might recognize are MMS, which I worked for operations on for a little while over at NASA Goddard, the James Webb Space Telescope, the ISS, International Space Station, and a whole bunch more. So we're going to go ahead and start taking a look at FreeFlyer itself. So I've got some pictures, and I'm going to sort of be bouncing back and forth between my slides and FreeFlyer so that you can get the full picture. So this is the home screen. When you open up FreeFlyer, this is what it will look like. At the top left, we've got our menu bar. This includes all of your kind of typical options that you would see on any application, really. On the left, we've got quick tasks. So these are two really handy buttons that let you create a new mission plan, which is what a chunk of FreeFlyer code is called. You can browse sample mission plans, and FreeFlyer comes with over 200. I have no idea how many anymore. We have a whole bunch of them. And those are great examples that you can work from. We've got a lot of resources for helping you learn about and learn to use FreeFlyer. On section 4 here, just recent files. It's pretty self-explanatory. In the middle section, we have our demonstration mission plans, which are kind of our big, flashy, showy demos. And they are some of our cooler mission plans. I'll show one of them in a minute. Down at the bottom, we've got our sample mission plans that include new features. So in this last major release, 7.5, we added the terrain capability. So a lot of these are focused on modeling contact analysis while accounting for local terrain like mountains or canyons or things like that. Over on the right, we've got our contact information, which you'll see a few times throughout this presentation. And then, of course, our tip of the day, which changes every day. Well, it doesn't change every day, but it changes through a cycle on your FreeFlyer home screen. So I'm going to go ahead and just pull up FreeFlyer. Here's what it looks like on my screen. We see all these cool sections I was talking about. And I'm going to open up one of my favorite demo mission plans just to give you guys a teaser for what FreeFlyer looks like. This is the Lunar Gateway mission plan. So spoilers, it's one of my favorites because I wrote it. Yeah. And it's modeling a really cool mission, the Lunar Gateway, that NASA is planning for, I think launch is intended in 2024 at this point. So this is in a really cool orbit called a near rectilinear halo orbit around the moon. And we're taking a look at it in a few different frames. A rotating view with the Earth and Moon, a Moon-centered inertial view, and an Earth-centered inertial view. And this is just a really great example of some of the cool visualization, contact analysis. We can see we're communicating with ground stations on the Earth, a bunch of different things that you can do in FreeFlyer that create some really impressive visuals and also just really help you to kind of understand the concepts behind orbital dynamics. Also, fun fact, the orbit tail is drawn in my wedding colors, Easter egg. So we're going to jump over to the control screen in FreeFlyer. So once you've opened up a mission plan, you'll have all of these options at the top: home, control, output, and notes. And on the control screen, that's where we build up our mission plan. So on the left-hand side, we have the object browser, which contains all the objects that you're working with in your mission plan. You can also create them in script, which we'll talk about a little bit later. On the right-hand side, we have script elements. These are drag and drop commands that you can pull into your mission sequence in the middle to build up your analysis. At the top, number 4 here, we have our navigation bar. This lets you run the mission plan. The green check mark is a syntax checker, and you can record the mission plan if you'd like with the video icon. We've got the undo and redo buttons. You can also use shortcuts to undo and redo in script, but these can be used to undo actions in the object browser or in the mission sequence itself. And down at the bottom, we have our status bar, which will just show you whether the mission plan is running, has completed execution, and how long it's been running for. Talking a little bit more about the control screen. So I mentioned freeform blocks and freeform scripting, or rather FreeFlyer scripting. So one of the coolest things about FreeFlyer is that it has a scripting language, its own scripting language. So this is a little bit different from some other space-related applications that you may have seen, like SDK, which are entirely GUI-based. FreeFlyer has a scripting component, which I find to be extremely helpful for organization and just for learning a new tool. It's really helpful to have something that you can write out like any other scripting language. People who are familiar with MATLAB tend to pick it up really quickly, so that's another great tie-in. So the way that you set up a freeform block is just drag and drop one in from the script element side into your mission sequence, and you can double click to open it up. You can move it all over the screen, like this one has been set to the bottom of the screen, and then you just type directly in there to create objects, perform commands, call methods, all kinds of things. So if we look at the control screen for Lunar Gateway, this is a pretty complicated one. It has a lot of objects in the object browser, but then we can really easily organize it through our freeform scripting blocks. So if we open one up, we see FreeFlyer script typed in there. On the output screen, which we already saw in FreeFlyer when we ran the Lunar Gateway mission plan, you get your workspace tab. So a new workspace tab is generated every time you run the mission plan. That status bar down at the bottom gets updated. And then you can hop back and forth between the control and output screens just by clicking the buttons up at the top. And additionally, replay output which is new as of a very recent version of FreeFlyer, to replay your mission plan over again after it's finished executing one time. So that's really nice because you don't need to start over every single time you want to see your output. Finally, we have the notes screen. This is just a handy little tab that lets you take notes directly in with your mission plan about whatever it's doing, anything that you might want to write down before passing it on to the next person who's working on it, anything like that. So that's kind of the whirlwind introduction to FreeFlyer. I want to pull my chat window up. There it is. I'm going to stick it over here. That's kind of the whirlwind introduction to FreeFlyer. So I'll give a second for anyone to jump in with any immediate questions. And if not, then we'll just proceed right into our Astrodynamics intro. You guys are allowed to unmute, by the way, if you have a question, as well as posting in the chat. All right, we will forge ahead. So the main thing to know about Astrodynamics is that it's actually not that hard. It sounds really scary, but the basic math is actually really straightforward, especially when you're working in a simple system like a two-body problem. It basically requires just a algebra, geometry, and some super, maybe very simple calculus that you don't even really need because you can Google the equations if you need to. But for true understanding, you should probably take a calculus class. So the problem with these, with astrodynamics in general, is just visualization. Space is really big, and so it's hard to think about, you know, how does this look actually in space related to my my planet or my spacecraft or anything like that. So that's where tools like FreeFlyer can come in handy because it helps you put kind of an image to the problem that you're trying to solve. I see a question in the chat that says, where's the control screen? So let me just pull that up real fast. So for one thing, you won't see the control screen if you don't have a mission plan open. So if I close that, we won't see it here. But as soon as you open a mission plan, whether you create a new one or open an existing one, you get those three additional screens: control, output, and notes. You're welcome. All right, so we're going to start with the total basics, Newton's laws. So if you've taken physics, you've probably seen these before. If not, then you're going to learn, and they're not very hard. So that's awesome. So the first law is known as the law of inertia. And that's saying any object at rest will stay at rest, or any object in motion will stay in motion unless acted upon by an external force. I know there are like songs that you learn for it early on in your physics career, but man, I feel old now and I don't remember any of them. So in the absence of any forces, basically all that's saying is that an object will maintain a constant velocity. So an important thing to remember for orbital dynamics is that velocity is a vector, meaning it has both direction and magnitude. So why is this important? Because if you see a spacecraft moving in a circular orbit, you might think, well, that's not a straight line. It doesn't have, it has nothing going on. Like, what's going on? Well, that's because the force of gravity is acting on it. For an object with constant mass, moving on to our second law, it's just F equals ma. Force is equal to mass times acceleration. Don't have a lot more to say there. You can take it up with Newton if you have an issue with that. And then finally, for every action, there's an equal and opposite reaction. So that's the same thing as saying, you know, oh, if I'm standing on the floor and the floor is pushing back on me, I'm not going to fall into the center of the earth. Fantastic. So kind of analogous to Newton's laws, orbital dynamics has Kepler's laws. So we have three laws again. I don't know, something about three, it's a magic number. And Johannes Kepler developed these laws after observing the motion of stars in our solar system, stars and planets. So the first one is the law of orbits. And all this states is that all planets move in elliptical orbits with the sun at one focus. So we've got a picture over here. Here's the sun. This is obviously a very dramatized version. This is a highly elliptical orbit. Most planets have orbits that are much closer to circular. But all we're saying here is that all planets in our solar system move in this shape. The second law is the law of equal areas, which just states that if you were to draw a line connecting a planet to the sun, that line would sweep out equal areas in equal amounts of time. So if we have a planet that moves from C to D, this amount of space is going to take the same amount of time as moving from A to B, and it's going to sweep out the same area. So another way of saying this is your planets move much faster when they're closer to the object that they're orbiting. Finally, we have the law of periods. This is just an equation stating that the square of the orbital period, written as t, is directly proportional to the cube of the semi-major axis of the orbit. And we'll talk a little more about the semi-major axis in a bit, but I have written down the equation over here on the right-hand side. Another really important concept of astrodynamics, unsurprisingly, is gravity. So we'll take a second to talk about gravitational force and potential energy. So the force due to gravity is just the force that attracts any two objects with mass. So any massive object exerts a gravitational force on another massive object. I'm exerting a gravitational force on you right now. However, I'm really far away from you probably and pretty small compared to the planet that we all live on. So you probably don't feel it. The force due to gravity can be defined as F equals gmm over r squared, where F is the force, g is the gravitational constant, m is the mass of a primary object. In orbital dynamics, that's generally a planet or a star. Little m is the mass of your secondary object, often a satellite, and r is the distance between the two objects. Over on the right-hand side, we've got a little graphic created in FreeFlyer, might I add, of a gravity well below the Earth. So this is drawing the Earth's force due to gravity on an object with mass little m at any point. And it's scaled accordingly to make it look, nice. But this is how it drops off as 1 over r squared as we leave further away from the Earth. By integrating the force equation, so this is like the tiny, tiny bit of calculus, we obtain the expression for gravitational potential energy. So potential energy is defined as the integral of f dot dr. And if we integrate that from infinity, where the force due to gravity is 0, up to our current position r, we get the expression for gravitational potential energy, U equals minus gmm over r. So this one is proportional to minus 1 over r, while force is proportional to 1 over r squared. So another really important concept is the Keplerian orbital elements. And this is kind of the easiest way to describe your orbit. So we've got 6, A, E, I, Ran, W, or omega, and TA, or true anomaly. We're just going to talk briefly about each of them, and then we'll explore some of them in more detail when we're working in FreeFlyer later. So the semi-major axis is the distance from one end of your orbit to the other. So if this was a planet at the focus of an ellipse, the closest point is called the periapsis, and the furthest point is called the apoapsis. Eccentricity, E, defines how elliptical your orbit is. So for a circular orbit, E equals 0. For an elliptical orbit, E is somewhere between 0 and 1. And then if E equals 1, you have a parabolic orbit. And if you have an E that's greater than 1, you end up with a hyperbolic orbit. Those two, the semi-major axis and the eccentricity, define the shape and size of your orbit. The other 4 over on the right-hand side define the orientation of the orbit. So we've got a kind of confusing looking diagram up here at the top, but it's not too crazy. The inclination I is the angle between the plane, reference plane, we can call it the equatorial plane for Earth, and the plane of your orbit. Right ascension of the ascending node is the rotation of the ascending node point about from the reference direction. So the reference direction for Earth is typically the vernal equinox. The ascending node is where your orbit plane crosses the equatorial plane. And that angle is just measured from that reference direction eastward around to where the orbit plane crosses. The argument of periapsis is the angle from that point where our intersection is up to where the periapsis of the orbit is. So this here would be the shortest point in the orbit between, or the shortest distance rather, between your spacecraft and the planet or star. That can be written as W, as it is in FreeFlyer, or as a little omega. And the true anomaly just dictates where you are currently in your orbit. So that's measured from the argument of periapsis point to your current location. So it changes as you travel around the orbit. So now that we have our Keplerian orbital elements, we've got one more important equation that I want to go over before we move on. And that's called the Vis-Viva equation. So there are a lot of different ways to derive the Vis-Viva equation. We're not going to go through a full derivation here today, pretty much just presenting it, but this is essentially the derivation that's available on Wikipedia. So you can go look it up if you're interested. So recall that kinetic, yeah, go ahead.
We have a quick question in the chat about omega. I'm going back a slide.
I can go back a slide. Oh yeah, I do see that. Okay, is omega always the greater than 180-degree angle measuring to the second intersection of the planes? Ah, great question. So this is the ascending node. So what that indication is where the spacecraft is traveling upward. So where it intersects the plane and is traveling upward. So if your spacecraft's traveling along the orbit and it's going up on this side and down on this side, this one's the ascending node. That's a great question. The other one is called the descending node. But for the purposes of defining the orbit, we always use the ascending node. So if we were going the other way around the orbit like this, I think you all can see my mouse. Whoops, I clicked. Oh no. If we were going this way along the orbit, then this one would be the ascending node, and this one would be the descending node. Great question, and thank you, Michael. So getting back into our Vis-Viva equation, once again, lots of different ways to derive this. This is a super simple one, so I like it, and it's on Wikipedia, so it's really easy to find. So remember that kinetic energy from your physics class can be written as 1/2 mv squared, where v is the velocity and m is the mass of your object. By conservation of energy, your total energy is always equal to your kinetic energy plus your potential energy at any point in the orbit. So we can actually use this to solve for the Vis-Viva equation. What we can do is set the total energy at periapsis of the orbit and the total energy at apoapsis equal to each other. So in this equation, where the subscripts A and P are denoting apoapsis and periapsis, we have E equals kinetic energy 1/2 mva squared plus potential energy, which remember is negative, so minus gmm over Ra equals the same thing, but at periapsis. You can divide out all the little m's, use some algebra, use conservation of angular momentum. So that's just the statement that at periapsis and apoapsis, your velocity and your position are going to be perpendicular to each other. So your angular momentum can just be written as r times v. Rather, your specific angular momentum can just be written as r times v. You can set those equal to each other because that's conserved as well. And recall that the semi-major axis is, or rather, the total distance between periapsis and apoapsis is 2 times the semi-major axis, which I think I might have said wrong earlier. I apologize. And we can rearrange this to yield the Vis-Viva equation. So this gives you the velocity at any point in your orbit. If you have r, your current position, and you know a, the semi-major axis, then you can solve for v, your velocity. This is important for one of the examples we'll be working later, because it makes it really easy to solve for things like maneuvers and how much delta V you need to apply to change your velocity to turn into a new orbit. Okay, so that brings us to the end of our crash course in orbital dynamics. Do we have any questions before we jump into our FreeFlyer examples? All right, sounds good. And especially if this is new to you, I definitely encourage you to read through our FreeFlyer University guide, which I'll pull up in a second, on your own time as well. We have a question in the chat. What is RAN? So the right ascension of the ascending node is that concept we were talking about earlier. And that's the angle from our reference direction around the equatorial plane or reference plane to the point where the orbit intersects that plane and the spacecraft is moving upward. So ascending rather than descending. These can be written in a lot of different ways. In FreeFlyer, it would be pretty hard to write Greek letters in your code. So we just write RAAN to represent RAN rather than having to type a capital omega. But in your classes, you'll probably see it written with lowercase a, lowercase e, lowercase I, and the Greek letters capital omega, lowercase omega, and nu. And yeah, I definitely said this wrong earlier. The semi-major axis is half the distance between the two furthest points of your orbit. So my apologies if that created any confusion. Does it matter that ellipses have two foci for orbital dynamics? Great question. I suppose it matters, but you're almost never going to find something at the other focus because you just have one that you're orbiting. So essentially, in an orbit, you have the sun or planet or whatever your central body is at one focus of the ellipse, and the other one is just blank. There's nothing there. Just empty space. You are welcome. All right. So let's open up FreeFlyer and get working on some examples. That's the fun part of this workshop, right? Is actually working in FreeFlyer. So first, I'm just going to show you guys where you can find the university guide. So let me open up my web browser here. Can ignore all of my bookmarks. There are many. So this is the AI Solutions website. It's just ai-solutions.com. And you guys have all seen this already because you've registered for FreeFlyer accounts and you've accessed your FreeFlyer login page at the top right. Also on this website is our university guide. So you can go over to FreeFlyer and check FreeFlyer University. This contains information about our university program, which we'll talk a little bit more about later as well. But essentially, FreeFlyer is free for all university students. So if you're interested in using it in any of your classes, talk to your professor, use it for a project, get in touch with us, we'll hook you up. The university guide, which is available here, just in the middle of the page, this just scrolled down, contains a bunch of tutorials and examples, kind of like what we're doing today. It walks you through concepts of astrodynamics using FreeFlyer. So you don't get my lovely voice narrating if you just look at it on your own, but it is available right here on the website for anyone to look at. And you don't even need to log in, so you can see this without even having an account. You can also download it. I've already done that, so I'm going to open it up as a PDF just so that it's a little bit easier to look at while I'm sharing my screen. And it's over on the other screen. I'll bring it down here for everybody. Great. So today we're going to work through a couple of different examples. First, we're going to talk through our orbital elements tutorial. So we just learned about those, and we're going to look at what they can be seen as in FreeFlyer. We'll just go over the semi-major axis and eccentricity today in the orbit's shapes and sizes section. But if you're interested in the other 4 as well, I'd encourage you after this workshop, or maybe tomorrow if it's nighttime, to take a look at the orbit orientation section as well. We're also going to go through the first maneuvering tutorial called a Hohmann transfer, which is a very simple maneuvering example and kind of a really helpful one for understanding how maneuver planning works. So without further ado, we'll jump into our first section on orbit shapes and sizes. So first, we're going to talk about the semi-major axis. That's generally referred to as SMA or simply A. And again, that's the distance from the center of the ellipse, not the whole thing, to the longer end of the ellipse. In a circle, the SMA is going to be equal to the radius. So the semi-major axis can help you also determine different properties of the orbit, like the orbital energy and orbital period. Remember Kepler's third law? We saw that the period squared is proportional to the SMA cubed. So this is the way that the FreeFlyer University Guide examples are all structured. You're presented with a problem and then given step-by-step instructions in FreeFlyer to work through that problem and build it up all by yourself. So let's begin. First thing we're going to do is open up a new mission plan in FreeFlyer, and we'll just save it as SMA period. So again, I'll be jumping back and forth here between FreeFlyer and the University Guide examples, and you guys are welcome to follow along. Close this thing I was working on. So we're going to create a new mission plan, and once again in FreeFlyer, that's up at the top left over here. You can also click this icon at the top if you prefer. First things first, I'll go ahead and save this as SMA period, and hit save. Now I've got a brand new mission plan ready to work with. The first thing we're going to do is create a new spacecraft object through the object browser. So this will be new for everyone if you haven't used FreeFlyer before, so we'll go through pretty slowly, step by step. And if anyone has questions, again, just pop up by unmuting yourself or type in the chat. So over in FreeFlyer, in the object browser, that's one place that we can create new objects. We can also create them through FreeFlyer script, but in this example, we're just going to create ours in the object browser. So you can add a new object by clicking the Add button and then selecting your object type, or just by right-clicking anywhere in the object browser window and selecting Add. And we're going to choose Spacecraft. But just so you're aware, there are a lot of different objects in FreeFlyer, and you can look at all of them. It's very exciting. So after we create our spacecraft, we can double-click on that object to bring up the object editor. So this window shows a little preview of our spacecraft in its current orbit and has all of the different properties of the spacecraft. So you can change its orbit, attitude, physical properties, the color, we'll do that. And a lot of other important things like the propagator. So you can change what integrator is being used to propagate your spacecraft forward in time. You can change the force model. So you could set your Earth up as a point mass, which is what you would typically work with in a school example, or, you know, as a really complex gravity model with drag and lift and all sorts of things. You can add a bunch of different subsystems, tanks, thrusters, sensors. All of those can be added onto your spacecraft, and then they have properties of their own as well. And you can perform orbit determination, which is a fairly complicated topic that we'll go over another day. So I'm just going to go back to the first page, the orbit page here, and check the instructions for our example. So the first thing we're going to do is configure our Keplerian orbital elements. So there are a lot of different element types. Cartesian elements are kind of an XYZ sort of situation where they're all just referenced from a specific reference frame called MJ2000. They're a little bit tricky to work with. Oh, that's a great question. Is there a reason you wouldn't see orbit determination in that screen? So orbit determination is a mission tier feature of FreeFlyer. So FreeFlyer has two different tiers, mission and engineer. So actually all of you guys won't see the orbit determination screen because you have student licenses, which are the engineer tier. Orbit determination is a topic that you typically need when you're working in operations. So for students, if you're in a special case where you do need that, we'll work with you, but most of you won't at this point because you're just working on design problems. Good question and good catch because I tend to forget that I'm not working with an engineer tier license. Awesome. You guys are also polite. You all thank each other after the questions. So nice. So in our object browser, on our spacecraft editor, we're going to change our element type to Keplerian, and those are the orbital elements we were just talking about. And we're going to configure these 6 orbital elements. So we'll set a semi-major axis of 7,000 kilometers, and then everything else is going to be 0. So it's going to be an orbit in the equatorial plane. It's going to be circular, and we're just going to put our spacecraft right at the beginning of it. A periapsis isn't really well defined for a circular orbit, so that doesn't mean that much. But just for the ease of use, we're going to make them all 0. So we're going to hop over to FreeFlyer, change this element type field in our spacecraft object editor to Keplerian. And now we'll see that our orbit definition has changed to show us our Keplerian elements. And we'll go ahead and edit these to match what we saw in the guide. So A is going to become 7,000. And you'll see your orbit change as you input each element. This is a pretty small eccentricity anyway, but we're going to go ahead and change it to 0. Our inclination will also be 0. Right ascension of the ascending node will be 0. The argument of perigee will be 0. And the true anomaly will be 0. So here's our circular equatorial orbit. I see a question in the chat. Is there any meaning behind the default orbit parameters? No, it's just a generic low Earth orbit. So the orbit is fairly typical for a lot of satellites in the low Earth orbit regime, but it's nothing special. It just looks nice. Nothing fancy. Once we've got our spacecraft orbit configured, we can just hit OK to exit out of the spacecraft editor. All right, great. We made a spacecraft object. How awesome. You guys are FreeFlyer experts. So the next thing we're going to do is clone that object. So all that work you just did, you don't need to do it again. We can just clone it. So we're going to clone spacecraft 1. After we do that, it'll call itself spacecraft1 _ copy1, which is a pretty useless name. So we'll rename it spacecraft 2. We'll set the semi-major axis to a different value of 15,000 kilometers, but we'll leave all the other orbital parameters the same. And we'll make it green on our visualization page. So I'm going to go ahead and do that. So in the object browser, you can right-click on spacecraft 1 and select clone. We see it's named itself copy 1. That's kind of silly. We'll just double-click to open that up. You can rename it up in the top right corner under the spacecraft name section. So we'll call it spacecraft 2 because that makes sense. And then we can see that because we cloned it from spacecraft 1, the element type is already set to Keplerian and it already has all of the parameters that we set for spacecraft 1. So the only thing we're going to change is the semi-major axis, which we will set to 15,000 kilometers. And we can see in our little preview window here that the orbit has grown because the semi-major axis defines how big the orbit is. Once you've got that all set on the orbit page, we're going to travel over to the visualization page. And we're going to change this spacecraft's tail color to be green. So you can choose from, you can really choose whatever color you want, but I'm going to choose green to stick with the example. You can choose from these colors, or you can use the color picker to define a custom color. The most exciting part of any mission plan, really. That's not a good green. I'll use this one. And once you've configured your SMA on the orbit page and changed the color on the visualization page, you can just hit OK to save. We're going to make one more spacecraft, so we're going to have 3 in total. This time we're just going to clone spacecraft 2 and rename to spacecraft 3, unsurprisingly. And we're going to change A to be 42,164 kilometers, which might seem like a really random number, but we'll see why that might be important in a little bit. So let me try to remember that while I come over to FreeFlyer. We'll clone spacecraft 2. So you can also rename your objects right from here by right-clicking on them, or handy shortcut, you can just press F2, just like you would to rename a file in Windows Explorer. So I'll do that this time. Just call this spacecraft 3. Then I'll double-click. And we can see, oh, it looks just like spacecraft 2 looks now. It's green and it's in this 15,000 kilometer orbit. We're going to change our SMA to 42,164 kilometers. When we do that, we can see, wow, our orbit has really expanded. You can zoom in and out in this window by right-clicking and dragging. You can also left-click to rotate around. And now we're pretty far away from the Earth. On our visualization page, we're going to once again change the color. So I'm going to choose yellow because that is what the guide suggests. But again, you can really choose whatever you'd like. And hit OK to save. All right. We're going to configure one more thing through the object browser before getting into our mission sequence, and that's going to be a view window. So we'll create a new view window by right-clicking in the object browser. This is just one type of output that FreeFlyer offers, simple 3D view. We'll double-click on the view window to open the editor. We'll check all of our spacecraft to make them visible in the view, and we'll show their names. We'll change the history mode to unlimited so that we can see all of their orbit tail. And then we'll set up an inertial viewpoint. So let's jump back over to FreeFlyer. And in our object browser, we'll say add a view window. So these 4 are pretty common objects: spacecraft, ground station, variable, and view window. So they get to be right at the top. But again, you can see the full list in the all alphabetical section, or some that are kind of grouped, for example, by output in some of the other sections here. Hopefully showing that gives kind of an idea of the scope of FreeFlyer, because it can do a whole lot of stuff. After creating our view window, double-click to open up our editor. So we're going to check these boxes for each of our spacecraft to show them all in the view. Then you can either Control-click or Shift and click, or just click on the spacecraft word to select the whole group of spacecraft objects. And we're going to check the Show Name box for all 3 of them. So this will just show their names in the view, make it easy to keep track of which is which. We're also going to change the history mode here from wrapped to unlimited. So all this property does is say whether you want to only draw a certain number of points in your orbit tail, or if you want to keep drawing points for as long as your spacecraft is propagating. So we're going to do that this time by selecting unlimited, and then you'll see that tail length option goes away. Then if you click on each of these individually, you should see that the Show Name checkbox is checked and the history mode is unlimited for each of them. on the left-hand side, we'll move down to the viewpoints page. And we're going to change our reference frame from body fixed to inertial. So body fixed just means that we're rotating with the Earth. Our frame is fixed to the Earth, which is our central body. And inertial just means that we're looking at an inertial reference frame. So we'll see the Earth turning in the view, and we'll see our orbit as it would be viewed in an inertial frame, which is kind of how we tend to picture them in our heads. So once you've got those configured, just hit OK to save. Great question in the chat. What would be a benefit of body fix? Well, there are a lot of different benefits. So a body fixed frame is a great way to think about an orbit ground track. So what part of the Earth you're traveling over at any given time. And FreeFlyer has a 2D map feature that makes that really easy to see. Another good thing of a body fixed frame is going to be related to our spacecraft 3, which we'll look at. I don't want to give away the big surprise just yet, but it gives you an idea of if you're standing at one point on the Earth, you can see this spacecraft or you can't see this spacecraft, as opposed to kind of looking at it from a bird's eye view. So a body fixed frame is always good kind of for, realistic contact analysis and things like that. Whereas an inertial frame is really good for kind of a big picture view while you're learning these concepts. All right, we're going to jump into building our mission sequence now. So I'll give everyone just a second to pipe up if you have any questions about the setup in the object browser before we do that. And also I'm thirsty, so I'm going to take a drink. Color changing cup from Starbucks, by the way. Fancy. I was very excited to get it. All right, sounds like everybody's following along great. So we're going to start building up our mission sequence, which is that middle portion of the screen. First thing we're going to do is drag and drop a while loop into our mission sequence, and we'll change the stopping condition to spacecraft 1.elapsed time is less than 2 days. And we'll talk a little bit more about what that means as we build it up. Then we'll drag 2 step commands into the while loop. We'll edit the second step command, and we'll talk about that as we do so. And then we'll get back to our instructions for more. So over in FreeFlyer, the first thing we'll do is drag and drop a while script element into the mission sequence. So on the right-hand side, you have the list of all the different script elements. These are just the ones that are available through the GUI. So remember, I've been talking a bit about kind of the power of FreeFlyer scripting. There's a lot more functionality that you can use in FreeFlyer script, but the script elements are a great way to get started. So we're going to drag and drop this while loop into our mission sequence. Then, just like in the object browser, you can double click on your while loop to edit the parameters here. So this is going to set up a condition, and we want our condition to be spacecraft 1.elapsed time is less than 2 days. So what this is saying is it's going to evaluate the elapsed time property on the spacecraft object. If some of these words are new to you, this is kind of the language of object-oriented programming. So FreeFlyer is a really good tool to learn that because it's not as complicated as some other object-oriented languages. And all of the method names are like really clear. So that's fantastic. But as I'm saying words like property and method and object, remember that you're learning programming language. So spacecraft 1.elapsed time evaluates how much time has elapsed since the first time this method was called. We're going to leave this as is, leave this less than symbol, and we'll change our condition to be 2 days. So a time span is a feature of FreeFlyer's nanosecond precision mode, which allows us to use really, really precise time values. We're not going to get into the details of that there because it's not that important. Just know that this is representing a unit of time, and that unit of time is equal to 2 days. So we'll hit OK to save. So now anything that we bring into the middle of this while loop is going to be evaluated while this condition is true, while the elapsed time is less than 2 days. So we're going to bring 2 step commands into the while loop. The first one will say step spacecraft 1. And then the second one, we're going to set up a step 2 condition to synchronize the epochs between spacecraft 2 and spacecraft 1. So let's go ahead and do that. So our script element over here on the right is called step. We'll just drag and drop. And this red line shows you where the script element is going to land. So we're going to put it in the middle of our while loop. And then we're going to bring another one in. And we will be editing this one. Goodbye, Amanda, in the chat. So our first one is just a command. It says step spacecraft 1. And what that means is that it will step forward in time along our orbit by our designated spacecraft step size, which you configure through the object browser. We didn't bother touching it. The default is 5 minutes. Our second one, we want to make sure that our second spacecraft, so we're going to change spacecraft 1 here to spacecraft 2, and we want to make sure that it stays synchronized at all times with spacecraft 1. Now it will, because we haven't changed the step size, so they have the same step size, but it's really good practice to set up your propagation like this so that even if you had different step sizes, your spacecraft would never get out of sync. So we're going to check the box that says step 2 condition, and that will bring up a new box here. We're going to change this parameter to set up a logical statement that says spacecraft2.epoch equals spacecraft1.epoch. So we'll change our object to spacecraft 2, and we'll change the property. There are a lot of properties on the spacecraft object, but we're going to use epoch, and that gives our current spacecraft time, what time it's at in the simulation. We're going to change this qualifier to a double equal sign. So instead of being less than or equal to, greater than or equal to, we're going to use equals equals, which just means equal to in programming world. And then on this last one, we want it to be equal to spacecraft1.epoch. So we'll change the type of item to an object property / method. The object is already spacecraft1. That's super convenient. And we'll change the property to epoch. And I'm just typing the letter E to jump to the E's because that makes it easier than scrolling through the whole thing. So your step 2 condition should look like this. Just give a quick pause for anybody to catch up. And then once you've got that all set, we'll hit OK to save. So that takes care of spacecraft 2. Our next instruction is going to be to do the same thing for spacecraft 3. So just like in the object browser, you can clone script elements. So we'll just clone that command that we just set up. And we'll step spacecraft 3 to the same epoch. Can we please repeat step 2? Yes, I can repeat step 2 for sure. I'm sorry that the audio cut out. This darn teleconferencing thing, man. So in this step, we just dragged a second step command into the mission sequence and then double clicked on it. We change the object that we want to step from spacecraft 1 to spacecraft 2. Check the step 2 condition box and then set up the following condition. So spacecraft2.epoch, choose equal equal spacecraft1.epoch. And I'm going to ask Michael to post a link to the university guide in the chat so that if anybody does fall behind, you can catch back up by following the example in the university guide, because that's exactly what we're doing. It's all right there. All right, so once we've got our spacecraft 2 propagation set up, we need to step spacecraft 3. We might have forgotten about it, but we do in fact have 3 spacecraft. Thank you, Michael. So we'll just right click on this command that we just set up and choose clone selected. So that'll bring the exact same command in here. You can also expand this if you want to see the whole thing. Just drag it around. And this is just stepping spacecraft 2 again, so that's not very useful. We want to change that to spacecraft 3. So we'll double click. And just a couple of edits here. We'll change what to step to spacecraft 3. And then the first part of the condition should be spacecraft 3.epic. And we'll leave this the same, equals spacecraft 1.epic. So what this is doing is making sure that all 3 of our spacecraft are going to be synchronized at all times, even if we had messed up and set them up with different propagator step sizes or something like that. That's not messing up. You might want to do that on purpose, but you want to keep them all synchronized in your view. So now we've got all of our propagation set up. That's awesome. But we won't actually see anything if we just run this right now. It'll just be blank and you will have no idea what's going on. So we need to create some output. And this is why we built our view window. So all we're going to do is drag and drop, we're on this step, drag and drop an update command into the while loop after our step commands. So I'll just take this update script element on the right and drag and drop it in right after our step commands. Now we're going to generate one more type of output. This is called a report. So we're going to use the report command to just report out our period, because remember, our SMA is related to our period. So the period is the total amount of time that it takes your spacecraft to orbit all the way around one time. So we're going to jump back into FreeFlyer and use a freeform script element to type out this command. Report spacecraft 1.period, comma, spacecraft 2.period, comma, spacecraft 3.period. So this is your first intro to FreeFlyer scripting. How very exciting. We'll grab this report command, or sorry, freeform element from the script element side. That's up at the top, it's the second one. Drag and drop that guy in under the update command that we just created. And we'll double click to open it up in a new window. So this is a freeform script block. You can change the name of it. I think the guide might have actually told me to change the name of it. Yes, it did. I wasn't listening to the instructions. So we're going to change the name to report orbital periods, because that's what we'll be doing. So that's a really handy feature of these freeform blocks. You can label them whatever you want, and that helps you keep your code organized. And then we're just going to type out our report command. So as you type, you'll see that you get a little drop-down menu of autocomplete options. So as I start typing the word report, it recognizes that I want to type report, and I can hit enter to autocomplete. And then I want to report the period for each spacecraft. So I'll start with spacecraft 1, again, taking advantage of that super handy autocomplete feature, which, by the way, is fantastic for saving time and also avoiding typos. When I type a period after spacecraft 1, I see all of the different properties and methods that are available on the spacecraft object. And there are a lot of them. So you can scroll through as I'm doing now using the arrow keys or just with your mouse. And every single one has a description that pops up when you reach that property. So I'm going to start typing period. And it tells me what's the period. Oh, it's the period which corresponds to the instantaneous unperturbed two-body Keplerian orbit. That sounds like a lot of silly words. It just means the amount of time that it's going to take the spacecraft to travel around the orbit once. And our units are going to be in minutes. So I'll hit enter to fill that out. Then a comma to add another one. Spacecraft 2 this time, dot period. And a comma, spacecraft 3, dot period. Then every line of FreeFlyer script ends with a semicolon. That tells FreeFlyer that you have completed that line of script. There's no more to it. That's the entire command. All right, so now we've got a mission plan. Awesome. So that's our report command. That should be the final step in our example. And your mission sequence should look something like this. It's shown in the university guide over here, and I'll also show it on my screen. We've got a while loop, 3 step commands, a view window update, and a freeform block to report our orbital periods. So once you've done that, you can save by either clicking the save icon or just hitting Control-S, keyboard shortcut. And then when you're ready, you can give your mission a syntax check if you'd like, to see if there are any syntax errors. For example, if I forgot my semicolon and did a syntax check, it would tell me, oh, you're missing a semicolon. Well, that's helpful. Thank you, FreeFlyer. Let me just add that back in. Now I passed syntax check, and my status message down at the bottom tells me, oh, the mission plan passed a syntax check. Then I can hit run. And now finally, we get to see the output of our mission plan. So we've got 3 different spacecraft in 3 different orbits, and we have our report windows telling us the period for each orbit. So, unsurprisingly, spacecraft 1 is in the lowest orbit with the smallest SMA, and it has the smallest period. Spacecraft 2 is a little bit bigger, and spacecraft 3 has an interesting period of 1,436 minutes. So you may not recognize that number, but this orbit that spacecraft 3 is in, I told you guys it was special. It's called a geostationary orbit. And what that means is that it's going to orbit at the same rate as the Earth, so about 24 hours. And now we can take a look at our body fixed view, and something really interesting might happen. I'm going to make this a little bit bigger by maximizing the window. If I zoom out here, this is our inertial view. So this is what the orbits would look like in an inertial frame. But if we go over here onto our output properties tab and change the reference frame to body fixed, it looks like spacecraft 3 disappears. But that's crazy, right? No, it's not crazy. It just stays at the same point above the Earth the whole time. So it's always looking at, what's that, kind of somewhere out here in the ocean. Not a super useful spot, but this can be a really useful orbit for a spacecraft that needs to stay above the same point in the Earth at all times. So there are some cool, fun orbits that you can learn about and explore by playing with these different reference frames. That Lunar Gateway one that we were looking at, it only looks that cool in a rotating frame, and it's really cool because it gives us a lot of communication opportunities with Earth, and it really is just a really useful visualization tool to understand what your orbit is going to look like and how it will be useful in space. So that brings us to the end of our SMA example. I'm going to give everyone just a minute to ask any questions. Make sure you save your work. I'm going to make one more comment while everybody's thinking of questions or thinking of not having questions. We notice that the period doesn't remain constant over here. That's because FreeFlyer is a real-world modeling tool. And so we can, in fact, set up our Earth to be modeled as a point mass, creating a perfect 2-body orbit like what the Keplerian elements truly describe. But if we don't, and we use a complex gravity model, as we've done here, the default is a 4x4 model, which I'll discuss at another time if we have questions on that. But that's just telling us kind of how fancy are you getting with your model, how high of fidelity is the gravity going to be. And so we see that these period values change across the orbit. They're not perfectly exactly the same the whole time. So this is another great way to kind of apply FreeFlyer to real life, making that transition from the classroom into the industry. Why does the radius change as I zoom in and out? It doesn't really. It just looks like it does because I'm getting further away. So as I come in, this radius, the distance from Earth, isn't actually changing. Oh, we're probably asking about this. No, we're not. That doesn't say radius. Whatever the question is, the radius of the orbit isn't changing, but as I get further away, the Earth is getting smaller and the orbits are scaling along with it.
Why is the radius changing in the status text?
Oh, okay, I see. Thank you for the clarification. See, I always look over here in the output properties tab, and it's called translation over here, and up here it's called radius. So that's the radius of our camera. So that's how far away is our camera from the center of our view. So the center of our view is the Earth, and we can zoom all the way into the middle if we really want to, but it's not very exciting. Our spacecraft are way out there. But that's actually a really great question, and something I'd like to point out is that all of these properties as well are configurable in script. And what that means in FreeFlyer is that you can make some really cool visualizations by like scripting changes in your radius to zoom in and out while your mission plan runs. We've got a blog post actually with some cool visualization tips and tricks that I definitely remember checking out or recommend checking out. I remember helping to write it. It was a blast. Got to make some fun movies. Yes, great questions. All right, so that's your first taste of FreeFlyer. We're going to move on into the next example. It's a little bit shorter because we're going to build off of what we already have. So next we're going to talk about orbital eccentricity. And if anyone has any questions, again, just keep posting in the chat. This is awesome. My blog post. It's not all me. I did do a lot of it, but it was really fun. So as a reminder, orbital eccentricity is the shape of the orbit. So how circular is it versus how stretched out is it? This doesn't affect your spacecraft's orbital period or its specific energy. So the orbital period is proportional to the semi-major axis, and orbits can have the same semi-major axis but different eccentricities, and we're going to see that in this example. So we're going to go ahead and keep working on the SMA period mission plan that we just made, but we're going to save it under a different name. So make sure that you save the existing one. And then we're going to change it. So I'll hit save to make sure I've saved that. Now we're going to just do a save as to make a new file. And we'll call this one, ooh, what do we call it? I forgot to check. Just eccentricity. And we'll hit save. Oh my gosh, hopefully you guys can't hear it, but it just started raining a lot outside my window. All right, so for this one, we're going to edit our spacecraft so that they all have the same SMA of 30,000 kilometers, but different orbital eccentricities. So we're going to change the E properties in that object editor to be 0.05, 0.25, and 0.7. Remember, a higher value of E means a more elongated orbit. So we'll come over to FreeFlyer. And we can just start clicking right on our spacecraft objects in the object editor. So we'll open up spacecraft 1, change A to 30,000 kilometers. This is not a special value, it's just arbitrary. And our first eccentricity is going to be 0.05. Double checking. Yes, it is. So if we hit enter or just click anywhere else in the screen, we'll see the little orbit preview adjust. And it's still a pretty circular orbit. That's a pretty small eccentricity. Once we've got that configured, we'll just hit OK to save. Then we'll open up spacecraft 2, set the SMA to 30,000. And this time we're going to change the eccentricity E to 0.25. And this time we should see a more noticeable change in our orbit. So remember, you can manipulate this window by clicking and dragging. And if we look at this from above, we can see now the Earth isn't quite at the middle because it's no longer a circular orbit. So it's at one focus of the ellipse. And if there was an imaginary other focus here, it would be about there where my mouse is. Maybe more like here. It's kind of hard to say. Once we've got that configured, we'll just hit OK. And we'll move on to spacecraft 3, which is going to get the same semi-major axis, 30,000. And this eccentricity is going to be really high. It's going to be 0.7. Goodbye, Rama. Thank you for coming. So that was a really big dramatic change when we changed that eccentricity to 0.7. Now we can see a highly elliptical orbit with the Earth at one focus. The other focus would be way over here. And we can see that at periapsis, or when it's the Earth, you can call it perigee or apogee, Latin. I don't know why they do this. When you're over here, you can call it periapsis, and that's the closest point to the Earth. And over here at apoapsis or apogee, that's the furthest point from the Earth. And just hit OK once you've gotten that configured as well. Now this time we're going to create a plot. So we're going to plot our spacecraft velocities. We're not going to bother reporting the orbital periods anymore. They're all going to be the same because it's all the same SMA. So we're going to delete that freeform script, and we're going to create a new one called plot speeds. And this time, the code's going to be pretty simple, but we're going to use the plot command to create a plot window. So the plot command, we just specify first our x-axis. So that's going to be spacecraft1.elapsed time, and then we'll convert that elapsed time to hours using the 2 hours method. And then on the y-axis, we're going to plot the velocity, or Vmag, so that'll be the speed, velocity without direction, magnitude of velocity vector, for spacecraft 1, spacecraft 2, and spacecraft 3. So let's go ahead and change that in our freeform script. So you can delete the whole freeform if you want to, but I'm just going to leave it there because that seems easier. I'm going to rename it plot speeds. And then I'm going to delete this report command and change it to a plot command. So this will be plot on the x-axis, spacecraft 1 dot elapsed time dot 2 hours, comma. Then we have 3 different y-axis values that we want to plot. So we'll have spacecraft 1 dot Vmag, and remember this handy bubble pops up to tell us, oh, this represents the instantaneous magnitude of the spacecraft velocity. So we'll have spacecraft 1 dot Vmag, comma, spacecraft 2 dot Vmag, comma, spacecraft 3 dot Vmag, and a semicolon to end. That's the whole thing for this one. So you should see a mission sequence that looks something like this. Got the 3-step commands are all the same, and the update view window, and then a freeform that is now plotting our speeds instead of reporting our period. Make sure you save your mission plan, and then you can go ahead and run. So pay close attention to when the velocity spikes, where each spacecraft is in its orbit in the view. Spacecraft 3 is a highly elliptical orbit. So as it zips around the sun down here, it's moving really, really fast. And so we see this crazy spike in the velocity. Whereas the other two are a little bit calmer. We definitely see some variance with spacecraft 2. You can highlight, or rather hover over the legend to highlight the one that you want to look at, by the way, in the plot. So we see a little bit of variance with spacecraft 2, which has some eccentricity. And then spacecraft 1 is just barely not a circle. So we're seeing the velocity doesn't change very much as we travel around the orbit. And then in our view, we're still in our inertial view, and we can kind of take a look at the shapes of these orbits and how they're all different. Fun interjection. one of the missions that I used to work on, the magnetospheric multiscale mission, is in a highly elliptical orbit. And it's also a formation flying mission plan. So there's 4 spacecraft that are super close together. So we have 4 spacecraft that are all in like really, really near each other, zipping around the Earth at super high speeds. And it was always a little bit stressful, but really exciting. All right. So that brings us to the end of the eccentricity example. Everyone make sure you save. Could we please explain the plotting process once again? Yeah, absolutely. So this is using a FreeFlyer script command to create a plot window. So over in FreeFlyer on our control screen, we just created a freeform called plot speeds. Since we already had one in here, I actually just deleted what was in the report period freeform from our SMA mission plan. And I changed it to say plot speeds up here. And then the plot command, you can see how it's highlighted in blue. That indicates that it's a command in FreeFlyer. Then we specify our x-axis is going to be spacecraft 1 dot elapsed time dot 2 hours. And then 3 different values on the y-axis, 1 for each spacecraft, and we're plotting the Vmag property to represent the spacecraft's current speed. This plot command just creates a simple 2D plot like what we saw, x and y, but you can also create polar plots. You can customize the plot by creating a plot window object. There are a lot of different things you can do to make it look a little bit more interesting. I'll leave that up for just a second for anybody who's catching up. All right. I'm going to save my mission plan. And then I'm going to come back to the university guide over here. And remember, the university guide is available online as well in that link that Michael sent. And it has all of these instructions written out step by step very clearly. So if you do fall behind and you want to take a stab at it later, I definitely recommend checking that out. So we have one more example that I want to walk through today. We're going to have to go a little bit quickly because we're starting to run short on time and I don't want to keep you guys here too long, but I do want to talk about a Hohmann transfer. So I'm going to come over to the maneuvering section of the university guide and click on the first example called a Hohmann transfer. So a Hohmann transfer is the most efficient transfer that your spacecraft can make to change the size of its orbit. So if you're going from one circular orbit to a larger or smaller circular orbit, you can use what's called a Hohmann transfer to minimize your delta V, or the amount of change in velocity that you have to make. So this is important because delta V determines how much fuel you need to use. And if you're a mission that doesn't have a lot of fuel budget, then you need to try to minimize your delta V. So this is a diagram of how the Hohmann transfer works. You can think of it as 3 different orbits. So your first orbit is the starting orbit, and it's drawn in green here. And at some point in this circular starting orbit, you perform a maneuver or apply some delta V to your spacecraft. This puts you into orbit number 2. So this is an elliptical orbit. We can see that if you were to go all the way around, it would look like this yellow ellipse here. But since you're trying to transfer to a higher circular orbit, you just travel around half of the transfer orbit and then perform another maneuver to interject into your final circular orbit. So there are 2 maneuvers here, 2 delta Vs, and our first orbit has a small semi-major axis, and it's a circle, so that semi-major axis is equal to R at all points along the orbit. And then your transfer orbit, the semi-major axis is equal to R, our initial parking orbit SMA, plus the final parking orbit, written here as R prime, divided by 2. So that's a really easy way to define the SMA of our orbit. It's just a simple equation. Then our final orbit is going to be orbit number 3, and it's circular again, and now we're in a higher SMA orbit. So we're going to talk through the calculation quickly, and then we're going to write it out in FreeFlyer. So this first section, called Calculating Hohmann Transfers in the guide, discusses how to apply the V-Spiva equation, remember that from earlier, to calculate the amount of delta V required to perform a Hohmann transfer. So the problem statement is up here. Our spacecraft has an SMA of 7,000 kilometers and is in a circular orbit. We wish to put it at a 20,000 kilometer SMA circular orbit, and we want to calculate the total amount of delta V required to transfer to this new orbit using a Hohmann transfer. So all of this, remember I promised you it's just algebra, is going to be based around the V-Spiva equation. So we're just going to be plugging in values for R and A to calculate the velocity at that point in the orbit. Mu here is equal to big G times big M, as it was written in our slides earlier, and it's called the standard gravitational parameter of the central body. This is different for every planet because big M is different for every planet. It's the mass of the planet. But for Earth, it's this value written here. So the first thing we'll do is find the velocity of the parking orbit. So remember, for the parking orbit, R is equal to 7,000 kilometers, and also A is equal to 7,000 kilometers because it's a circle. So plugging that in, we can find our velocity, which will be constant around the whole circular orbit. Next, we want to find the orbital characteristics of the transfer orbit. So remember, we have the radius of the parking orbit and the radius of our desired orbit. And so we can easily calculate the SMA of the transfer orbit by adding the two together and just dividing by 2. So here we've written it all out. A equals 20,000 plus 7,000 divided by 2. And now we have the SMA of our transfer orbit at 13,500 kilometers. So this is another value of A, and we can do the exact same thing. So we want to find the velocity at our first orbital insertion. So this first burn down here. So the current value of R is going to be equal to R from our parking orbit, and the current value of A is going to be equal to the SMA that we just calculated. So we just plug those in to our V-Spiva equation up here, and the result is 9.185 kilometers per second. Then we can easily calculate the delta V. So that's a really, really easy way to calculate how much change you need to apply for your maneuver. You just calculate the velocity in the original orbit and then the velocity at the same point, but in the transfer orbit, subtract them, and now we have a delta V value, and that's 1.639 kilometers per second. Feel free to plug this into your calculators at home if you want, but we're about to do it in FreeFlyer, so you really don't need to. That first burn will put our spacecraft into its transfer orbit, and then we just need to do the exact same thing to calculate the speed at the transfer orbit's apoapsis. So that, oh no, I scrolled way too far. So that is at the top of this diagram here. So now we're at the apoapsis of the transfer orbit, where R is equal to R prime, or the SMA of the desired final orbit. So we just plug all that in to our V-Spiva equation once more. It's a really useful equation. And we get our target velocity, or sorry, our apoapsis velocity is 3.215 kilometers per second. Finally, we do the same thing to calculate the velocity of the target orbit. In this case, R is 20,000 and A is also 20,000. That's our final circular orbit. Plug them in, we get 4.464 kilometers per second. So to make that jump from 3.215 to 4.464, we just subtract the 2, and now we have our second value of delta V. Finally, we have 2 burns in this whole transfer process, so we can just add the delta V's together to get our total delta V of 2.888 kilometers per second. So that was a bunch of algebra that I just talked through, which probably wasn't super exciting. Now we can do the fun part. We can create a mission plan to calculate this for us. So this is why we have computers, right, to do our math for us so that we don't have to do it in our head, because that would be tragic. So we're going to write a mission plan that will calculate the Hohmann transfer and also visualize it. And we should end up with something that looks a lot like that diagram, funny enough. So we're going to do all of this, not all of this, almost all of this, in freeform script. All of the calculations are going to be written in freeform script. So this is, if you've worked with MATLAB before, kind of similar to what you would do in MATLAB. You'll create variables to store numbers, and then you'll perform math with them. Easy peasy. So in our freeform script editor, we're going to start out with our initial freeform will be for user inputs, and we'll define our parking SMA, or initial SMA, as 7,000 kilometers, and the target SMA as 20,000 kilometers. So I'm going to go back over to FreeFlyer. First thing I'll do, first of all, make sure I've saved my eccentricity mission plan, and I'm going to close it using this Close Mission Plan button. This closes your mission plan without closing all of FreeFlyer, so you don't have to start it up again. And I'll create a new mission plan. And I'm going to save this one as Hohmann Earth-centered. So as the name might imply, this is going to be a Hohmann transfer between two orbits around the Earth, but this is also a type of transfer that can be used in heliocentric orbits to get from, for example, the Earth's orbit radius to Mars or something like that. Hit save. And then the first thing we're going to do is use that freeform script element to start typing some script. We'll drag and drop into our mission sequence, double click on it, and we're going to call this one user inputs. Now we've got two inputs, remember, our starting SMA and our target SMA. So we'll have, I'll go ahead and make that comment as well. So this is a comment in FreeFlyer, which you can create in a number of different ways. One way to comment out a whole line of code is to put these two slashes. And so what a comment is just a note in your mission plan that doesn't actually perform any function. It's just a note for the user. So kind of like that notes page, but right there in the script for you to look at. So I'll create that comment, but you don't have to, don't feel obligated. And then I'm going to create two variable objects. So this is the first time we're creating an object in script. So I'll start by typing the word variable. We can see it has this kind of light blue highlight. That means it's an object. We'll call it parking SMA. And we'll set the value equal to 7,000 kilometers. And we'll do the same thing for the target SMA. Variable target SMA equals 20,000 kilometers. So now we've created two variable objects, and we're going to use these to perform some calculations. Cool. So now we're going to move on to actually performing the calculations for the Hohmann transfer. So we're going to leave that freeform just as the user inputs. That's a really easy way to organize it and say, oh, this is what you can change to change the scope of the problem. We'll drag a new freeform block in for the next part, and we'll call it Hohmann calculations. And that's where we'll start typing all of these different calculations. So the first thing we'll do is get the parking speed orbit. These are the exact same steps that we did above in calculating Hohmann transfers. So we'll calculate the parking orbit velocity, then the transfer semi-major axis, the velocity of the transfer orbit at periapsis, and the delta V of the first maneuver. I'll come back into the instructions after that one, but then we're going to do the exact same thing to get the delta V of the second maneuver. and sum them up to get the total delta B. So go ahead and follow along in FreeFlyer. I'll come back out to my mission sequence and drag and drop a second freeform script element in. So you can have a bunch of these in your mission plan, and a lot of the complicated ones have a lot of freeform blocks, but it's really nice to be able to break them up into multiple different ones just to keep things organized. So I'll double click on this second one to open up my freeform script editor. And the first thing I'll do is name it something useful. That's a better idea than just jumping right in. We'll call it Hohmann calculations. So now the first thing that we'll do is calculate the parking speed orbit. And feel free to, you can copy and paste these out of the university guide if you'd like, or you can type them out. I'll type them out, but pretty quickly, so just keep an eye on and make sure you're following along. So I'll say variable, creating a new variable object once again, vpark equals. Then we're going to use the square root function in FreeFlyer. So FreeFlyer does have math functions, very nice. We'll say square root and a parentheses to pass arguments into the square root function. So you might have noticed this little bubble popped up with a description of what the square root function does. This appears for all properties and methods in FreeFlyer, like we've seen a couple of times before. I think this is the first time that we've seen a method that has multiple overloads. So this is telling you all the different types of things that you can pass into the square root function. So you could pass an array, and that would give you, that would return an array containing the square root of each element of that array. Or you can pass in a whole matrix, does a similar thing. Or you can do what we're doing and pass in just a variable. You can scroll through these using the arrow keys, which is what I'm doing here, if you ever want to look at the descriptions for all the different methods. But you do not need to be at the one that you're going to use in order to keep typing. I can do it just like this. So our Vice-Vivo equation says the square root of mu, that's going to be, go away. Sorry, my computer is bugging out. Earth dot mu. Why in the world? Guys, my FreeFlyer is showing me my IntelliSense bubble on the other screen and you can't even see it. Okay, hopefully that fixed it. Sorry, technical difficulties with screen sharing, the worst. Okay, it is popping up on the other screen for me, but it should be showing up on your screen for you. So we're just going to finish typing out this Vice-Vivo equation. Square root of Earth dot mu times 2 divided by parking SMA. Aha, I fixed it. Excellent. I don't know what I did. So that's 2 over R. And remember, in this case, R is our current position, and that's the exact same as our parking orbit SMA. Minus 1 over A. Oops, I typed A, but I meant parking SMA. Just close all our parentheses. And now, after much hubbub with me having things appear on the wrong screens at home, we have our Vice-Vivo equation written out to calculate the velocity of our parking orbit. Next step is to calculate the semi-major axis of the transfer trajectory. For this one, we'll create another variable. We'll call it trans SMA, because apparently writing out transfer would have been too many letters. Equals, and this time we're just going to sum the 2 other SMAs, the target SMA and the parking SMA, and divide by 2. So this will be target SMA plus parking SMA divided by 2, and a semicolon. Next, we'll use the Vice-Vivo equation again to calculate the velocity at periapsis of the transfer trajectory. So I'll create another variable called v trans peri. That's the velocity of the transfer orbit at periapsis. And in the guide, we define it right away, but I want to make it clear to you guys that you can also do this. You can create an object and just end it with a semicolon like this, and then manipulate that object later. So I'm going rogue. It's crazy. This is doing the exact same thing as defining the object right away, but I just wanted to show you a different way to use FreeFlyer script. This will be the square root of earth.mu times 2 divided by r, which again, we're at periapsis, so r is the parking SMA, minus 1 over a, which for our transfer orbit is trans SMA that we just calculated. Now we have 2 velocities, and that's all we need to perform a simple subtraction to get the delta V of our first maneuver. So I'll create another variable called dv1 equals v trans peri, velocity of the transfer orbit at periapsis, minus v park, and that's the velocity of our parking orbit. So we've just calculated the amount of delta V that we need to perform for our first burn in the Hohmann transfer. Give everyone just a second to catch up there, ask any questions. If you've fallen behind, give me a flag, and then we'll move on to delta V2. All right. So the next thing we'll do is calculate the transfer trajectory velocity at apoapsis, the target orbit velocity, the magnitude of the second delta V, and the total delta V. So we only have a few more calculations to have completed everything we talked about in the calculating a Hohmann transfer section. So we've got a few more equations. You guys can feel free to use copy and paste. Probably a good idea because the VCVA equation is similar every time. Just make sure you're changing all the arguments so that you have the right ones in the right spot. So we'll calculate velocity at apoapsis of the transfer trajectory, the velocity of the target orbit, and then subtract them to get our final delta V, and then the total delta V. So I'll just continue in the same free form. This is all still part of the Hohmann calculations. If you wanted to break it into 2 separate ones for dv1 and dv2, you're welcome to do that. I'm just going to keep all mine in one right here. So the next thing we'll calculate is the velocity at apoapsis of the transfer trajectory. So I'll create a new variable called v trans apogee, velocity of transfer orbit at apogee, equals square root. Here's our VCVA equation once again. Earth.mu times 2 divided by r, which is target SMA at our apoapsis, minus 1 over a, which is trans SMA in our transfer orbit. You guys may have noticed I'm also putting some spaces in between some of my different operations here. That's not required. The spaces are totally optional. It just helps with readability sometimes to kind of keep your variables all spaced out from each other. Helps it look a little bit more like an equation and less like a just wall of text. Next, we'll calculate the velocity of the target orbit, our final velocity calculation. So we'll create a new variable called vTarget. Use our VCVA equation one more time. Square root of earth.mu times 2 divided by r, which is the target SMA, minus 1 over a, which is also the target SMA, now that we're in our final circular orbit. Simple subtraction to calculate the delta V for the second maneuver. We'll create another variable called dv2 equals v target minus v trans apog. Oh man, I might want to rename that if we make updates to this thing. And the total delta V, we'll create a final variable, total dv equals dv1 plus dv2. Ah, yes. Good question in the chat about parentheses. FreeFlyer does follow the order of operations, but again, we're just kind of keeping things nice and contained and looking like they're math, just for readability. So I'll give everyone just a second to catch up in case there was any delay in typing that. We'll hit save, make sure you don't lose things in your mission plan. And then we'll get to the fun part. So this is all the math, right? And that's stuff we could do with our calculator, but we can also do in FreeFlyer. Now we can apply that math to cool spacecraft objects and impulsive burn objects in FreeFlyer to create a really awesome visualization. All right, I'm going to bring the guide back over here. So again, now we're moving on to the visualization aspect of this mission plan. So the first thing we'll do is, surprise, create a spacecraft object. You'll find that this is the first thing that you do a lot in your mission plans. And we'll get the spacecraft object, very similar Keplerian elements to what we've already been working with. Nice, simple, equatorial, circular orbit with an SMA of 7,000 kilometers. Then we're also going to make sure that that always lines up with our user inputs. So at the end of our Hohmann calculations script editor, we'll assign the value of spacecraft1.a, the semi-major axis property, to be equal to parking SMA, which is a user input. So we're going to set it up in the object browser just for consistency, but it will be overwritten if you change the value of parking SMA. And we'll talk through exactly how that works in FreeFlyer. So over in the object browser, which we're all totally familiar with now, we'll hit add or right click and select a spacecraft. Open that bad boy up. We'll change our element type from Cartesian to Keplerian. And then we're going to set our SMA equal to 7,000 and each of our orbital elements equal to 0. Question in the chat, are non-equatorial orbits common? Yeah, all the time. So depending on where your end destination is, you can be in a bunch of different inclinations of orbit. So an equatorial orbit is always just going to be moving around the Earth's equator in that plane. But if you needed to be in a different plane at some inclination, you would just change the I value here. And so if I changed this to 30 or something, we are now at a tilt above the equator. And this can be for a bunch of different reasons. One really common one right now is you have orbits with a bunch of higher inclinations that are trying to create constellations of spacecraft to cover a bunch of different latitudes on the Earth. So if you cover, or if your inclination is 0, you'll never see any latitudes above the equator. But if your inclination is higher, 30 degrees or something, then you'll see a bunch of different parts of the Earth between these two latitudes. And that ground track is going to cover a lot more of the planet. Great question.
Inclinations are also set by the spacecraft launch vehicle. Your launch site can only launch into certain inclinations. To see that in action, check out the launch site visualization sample mission plan in the FreeFlyer scripting sample mission plan area.
Yeah, great tip. Awesome. All right, so we've set up our spacecraft. Now we're just going to make sure that these user inputs, if we change this value, that it actually gets applied to the spacecraft. So at the end of our Hohmann calculations freeform, we're going to add a line that says spacecraft1.a equals parking SMA. So this assigns the value of parking SMA to our SMA property on the spacecraft object. Next up, we're going to add a view window. So we'll check spacecraft 1 under our available objects, show the name, change the tail to unlimited again. This is all stuff that we saw before. We'll go to our viewpoints and set up an inertial viewpoint so that we're looking at a Hohmann transfer the way it looks in that diagram. And then we're going to create an impulsive burn. So that's a new object for this mission plan, and it's used to model a maneuver. We'll change the attitude system, which we'll talk about as we create it, to VNB so that we can apply our velocity burn in the velocity direction. And then we'll create a second one just like it to set up burn number 2, because remember, there are 2 burns in a Hohmann transfer. So going back over to FreeFlyer, first thing I'll do in the object browser is create a view window. Double click to open that up. I'm going to check the box for spacecraft 1 and the show name box. And I'll change the history mode to unlimited. Finally, on the viewpoints tab, we're going to change the reference frame to inertial. I'm going to start moving a little bit quicker since we're getting towards the end of our time. So just keep an eye on that university guide if you're having trouble following along. But I do want us to get through this example because it looks pretty cool. Next thing we'll do is create that impulsive burn object. So coming back to FreeFlyer, in our object browser, we'll add, this is under the spacecraft related category, but if you don't remember that at any point, you can go to all alphabetical. And we'll create impulsive burn 1. So we'll double click on this. Again, this is going to allow us to model a maneuver for our spacecraft. So you can model this in a bunch of different systems. We're going to choose VNB, which is velocity, normal, and binormal. So that's just defining the axes of the coordinate system. We want to apply our burn in the velocity direction because this is a Hohmann transfer. So we're going to be changing this first element here in our freeform script. We don't need to make any other adjustments to this impulsive burn. Just set it to VNB and hit OK. And then we're going to right click and clone it, just like we did with the spacecraft objects earlier. And we'll rename this impulsive burn 2. If anyone has to leave, goodbye and thank you very much for coming. We'll keep forging ahead. So we've created 2 impulsive burn objects. Now we're going to drag and drop a while loop into the mission sequence. And this while loop is going to set up a condition, elapsed time is less than 2 hours. We'll drag and drop step and update commands into that while loop, just like we've seen before. And that's just going to propagate our spacecraft in its initial orbit for 2 hours, just so that we can see it in the video. So back to our mission sequence. Drag and drop that while script element. We'll double click and change the elapsed time to 2 hours. Once we've set that up, drag a step command into our while loop. It'll autofill step spacecraft 1. We don't have any other spacecraft that we need to synchronize this time, so we can just leave that just like it is. And we'll update our view window with the update command. That'll just propagate us in our initial parking orbit for 2 hours. Coming back to our instructions, we're going to start working with performing our maneuvers and getting into the transfer portion of the Hohmann transfer. So we'll change the color of our spacecraft tail. That'll just change the color in the view window. So that's cool. We'll start it out as red, it'll turn yellow, and then eventually green. Then, this is an important line, we'll assign the calculated delta V value to the impulsive burn. So what we're doing here is saying impulsive burn 1 dot burn direction 0. That means the first element of the burn direction array, which was those 3 values that we saw, velocity, normal, and binormal, in the object editor. We'll assign that to dv1, which we calculated in our script. Then we'll use the maneuver command to actually apply the burn to the spacecraft. So that's pretty cool. All you have to do is say maneuver spacecraft 1 using impulsive burn 1, and that change in velocity gets applied to your spacecraft in your propagation. Then we'll step the spacecraft along our transfer orbit to its apoapsis, and we'll visualize it. So this is called a while stepping loop, and it's just like a while loop, except it handles the propagation for you, so you don't need that extra step command. And that's pretty nice because that allows you to step it to a very specific condition, like the orbit apoapsis, which is what we'll be doing here, while keeping a smooth view window update with the update command. So in the interest of time, I'm going to copy and paste this out of the university guide, and I would encourage you guys to do the same. Oh, thank you, Adobe, for telling me about the PDF tool. So after our while loop, we need to drag and drop a new freeform in, and we can call it perform maneuver 1. Then we'll paste our script into the window. This isn't very nicely formatted, so I'm just going to fix that. Oh, there we go. So once again, we change our tail color to yellow. That indicates when the first burn is applied. We set the burn direction value to dv1, which we calculated in our Hohmann calculations freeform. We apply the maneuver, and then we step to the apoapsis of our transfer orbit. Moving along, we're going to drag and drop another freeform into our mission sequence and do basically the same thing for maneuver 2. So this time we'll change the spacecraft tail to line, or green, it's just bright green. And then we'll set the calculated delta V value, dv2, to impulsive burn 2 dot burn direction 0. We'll call that maneuver command again and report the total delta V values. So over in FreeFlyer, I'll have to copy and paste twice since this is in 2 different pages of my PDF. We'll create a new freeform block, call it perform maneuver 2. Change the color of our spacecraft tail, set up the delta V. Then we'll call the maneuver command and report all of our delta V values. Make sure you save your work as you're going along. We're almost done. Now we're all finished with writing script for the mission plan. We're going to add in one more while loop just to visualize the final orbit. So we'll set up a while loop with a condition that says elapsed time is less than 1 day. That'll just propagate it for a full day along its new orbit. And we'll use a step command and an update command to visualize. Back in our mission sequence, This is a good example that uses a combination of freeform script and script elements. So it's a really good one for kind of learning to use the FreeFlyer scripting tool. Did we say one day? We sure did. So we don't even need to do anything to this while loop. It already says spacecraft 1.elapsed time is less than 1 day. Drag a step command and an update command, and then we're done. So make sure to hit save, and then when you're ready, you can run your mission plan. So up at the top, we get a report window that displays all the delta V values that we calculated, and you can check these against our calculations that we did manually earlier in the first part of this tutorial. And then the good stuff is in the 3D view. We see our initial parking orbit in red, really close to the Earth's surface, our transfer orbit in yellow. The first burn is applied here when we change from red to yellow, and our final orbit in green, and the second burn is applied up here. And wow, that looks a heck of a lot like the diagram that we have in the university guide. So I hope that you guys enjoyed that Hohmann transfer tutorial. I know we had to speed up a little bit towards the end there because I don't want to keep you here all night, but it's a really good one. You can always go back and follow along it right in the university guide. Again, it's available there on our website. I just have a couple more slides for just regular old information that I'll walk you through super fast. This is a list of FreeFlyer's core capabilities, and there are a whole bunch here. I'll send these slides to Matt, and he can forward them along to everybody. We have some more detail about each of these in backup slides at the end of the presentation. So you can see that it just kind of covers the full suite of everything you could ever want to do for a space mission. For you all, if you're a university student, as we mentioned before, you can use FreeFlyer for free. So the university program is designed to help professors teach astrodynamics concepts using FreeFlyer, kind of like what we were doing today. And the university guide is a really great tool for kind of starting that process. It's based on the textbook Orbital Mechanics for Engineering Students by Curtis, which some of you may have used already in your classes. If you think it's something that your professors would be interested in, definitely mention it to them. Or if they just give you an option for a tool to use for a project in class, we think FreeFlyer is awesome, obviously. Hopefully you do too. We've got a lot of resources available, including some YouTube tutorials that are less astrodynamics focused and more FreeFlyer focused to kind of give you a better introduction to all of the different capabilities. You can earn your certification because don't we love taking more tests? How exciting. No, but this is a fun test. It's available online, and you can put that on your resume, apply for jobs, say that you have your certification. And all of you have probably done this already, but you just start the licensing process by registering on our website. Last note on this page is just that we have internships. We have some awesome interns on our team right now this summer, and that application is open every summer. It starts in December, so keep an eye out, or if you're getting towards December and you're just interested and want to know when it's coming out, you can shoot me an email or our team an email. Add our contact information. So on the left is our general tech support and sales distributions, which you can reach by email or by phone. And then on the right-hand side is my personal contact information as well as Michael's. So if you ever have any questions about FreeFlyer or about the university program or anything like that, you can reach out to us directly. You can reach out to these distributions, and we'll get you pointed to the right people, whatever you'd like. So I think that's all that I have. Thank you guys so much for hanging out with me tonight. This has been super fun for me. This is the first time we've done a workshop like this, so we'd appreciate any feedback that you have. Feel free to send it to us by email or by the WebEx chat or anything like that. And again, I'll make sure to get these materials to Matt so that he can forward them along to everybody.
Quick note, if your license is expiring soon, if we give you a short license just for the presentation today, if you contact us, we can probably extend that so that you have more time to play around with the FreeFlyer software. So just get in touch.
Yeah, absolutely. All right, everyone. Have a good night.